So today we want to introduce the notion of polar form for complex numbers. We've obviously determined that they can be represented in a way which is rectangular. So if we have the imaginary axis, if we have the real axis, which I'll call the x-axis, and the imaginary axis, which I'll call the y-axis, we define a point with an ordered pair of the coordinate b, a, okay? We also introduced the notion of reflecting that about the x-axis in order to find the conjugate, z bar. If this number is z, then z bar has the negative imaginary component. So we want to exploit our use of polar coordinates today, which I would hope you remember from multivariable or single variable calculus, in order to determine a polar way of mapping these points as opposed to using a rectangular coordinate system. Obviously, each will have its benefits, although, as we will see in future videos, the exponential function carries particularly important properties, which can be related to the trigonometric functions, which makes the polar form a lot more convenient for us. Anyways, let's get started and dive right in. So we want to start with the idea of the vectorized sum. So let's consider that I have the coordinate axis, and I have some complex number, which I will call z, and z can be represented by a vector, okay? So here is our number z, and we assign this to be a vector. This can be represented by a vector v, okay? So what we want to do now is we want to consider function or vectors of complex numbers. So what we're going to actually determine is that the vectors have the same properties as the complex numbers. If I want to add a complex number, I can simply apply the superposition principle, and I do the sort of tip-to-tail vector addition sort of thing. So if I have a vector, or complex number v sub 1, and I add it with v sub 2, it follows the same sort of addition rule where you add them tip to tail, and same with subtraction. So if I assign z sub 1 to be v sub 1 and z sub 2 to be v sub 2, then z sub 1 plus z sub 2 is equal to v sub 1 plus v sub 2. Now, however you want to define this vector is up to you. You could either use the polar form or you could use the rectangular form. This also leads to the consequence of the triangular inequality, of course having to do with the modulus of the complex numbers, but essentially what this says is that the magnitude of the hypotenuse needs to be less than the magnitude of the sum of the additive components. Anyways, what we can do now is we can consider the idea of the polar form in its generality. So what we want to look at is the advanced free parameters that we are going to add. So we have additional free parameters to use. If you consider, we already talked about one previously, which was the modulus of the complex number. So if I have the modulus of the complex number, I call that the magnitude of z, right? We had the magnitude of z, and we also have the angular sweeping value off from the real axis up to the angle of elevation of our vector, and that we call theta. So we now have polar coordinates that we can use. We can use x, y, or we can use r theta to represent r2, right? So because this is, again, a representation of r2. Anyways, what we want to do now is we want to consider our transformation equations that we have. So we have that x is equal to r cosine theta and y is equal to r sine theta. This should obviously be very simple. And of course, if I want to go the other way, if I want to find the value for r, I take the magnitude of z. That's a simple sum of squares. And then if I want to find theta, this is a little bit more complicated. I would think that you know that the way to find the tangent of theta, if you were in the fourth or the first quadrant, is you take the inverse tangent of y over x. However, this isn't going to cut it, considering that we do have like the angles which can be in the second and third quadrant. So what you kind of need to do is you need to apply the negative signs sort of ad hoc and use this arctangent formula as needed. Anyways, what we call theta is we call theta the argument of z. And what's important about the argument is that the argument can actually take many values, obviously, because theta can continue wrapping around, and multiple values of theta can represent the same angle of elevation above the real axis. So we call this the argument of the complex number. Now, the argument can actually be represented as a series or a sequence. Anyways, we call the argument of z to be equal to the initial angle of elevation from the real axis, plus or minus any integer multiple of 2 pi, right? Because if I go around 2 pi, if I go around 2 pi once, I get back to where I started. If I go around 2 pi twice, I get back to where I started. If I rotate the other way, I still get back to where I started. So you can see why there are infinitely many representations of the same angle of elevation. So the argument is going to be multi-valued. But we do rectify this by considering the argument, the principal argument of z, which we restrict to be between negative pi and pi. Okay, so this is requiring that our principal value for the argument is between this guy here. So we go from negative pi, and we go all the way around, and then we get back to pi. So it's still an integer multiple, or it's still a multiple of 2 pi, or an interval of 2 pi, but we restrict the principal argument. And when I say the principal argument, I really just mean like the important argument, the general argument that we use, as opposed to the series of arguments with the little a. So essentially the way that you can write this is that the argument of z is equal to the principal argument of z plus or minus 2 pi k. And I suppose I don't need the plus or minus. I could just have a plus and let k run over the integers and not just over positive numbers and 0. Okay, so that was a little bit of theory, but mostly algebraic, so I would understand that this would be fairly seemingly easy, although that said, some of the new notation could be a little bit wonky, considering the argument function. Okay, essentially now we want to just put it all together into the final form using this following definition. So given that a complex number can be written in the rectangular form z equals x plus iy, it can also be written in the form z equals r times the cosine of theta, which represents the real part, because if we're taking a right triangle, if we take a right triangle represented here, if this is our value of theta, this is our value of theta here, and this is our magnitude here, we obviously note that the height of it is equal to the magnitude cos theta, so r sine theta, and the displacement here is equal to r cosine theta. But obviously for the imaginary part, we add the coefficient I. So obviously we can factor out the r, so we get z equals r cosine theta plus I sine theta. We can reduce this function here actually to, I find this a bit arcane, but we can use this if we want to say that r times this cis of theta, okay, and cis function of theta just represents cosine theta plus I sine theta. So all of this is very cool. However, it's going to be replaced fairly soon once we determine that this whole business of cis theta is equal to e to the I theta. We'll talk about that later, and we'll derive it from Taylor's series. So in the next lesson, I want to consider some of the properties of the argument and its relationships with other quantities that we've discussed previously. And I would also like to discuss the idea of the modulus a little bit more, and also consider some examples. For example, like taking a complex number in the form of a plus ib and converting it into the actual polar form that we want to look at. And then, of course, we'll look at the actual exponential function. We'll derive Euler's identity in one of multiple different ways. Anyways, thank you very much for watching, and we will see you in the next lesson.